Our modern world is built upon an invisible foundation, the Internet.
It connects us, empowers us, and stores our most sensitive data.
Yet, despite its complexity and ubiquitous presence, this digital realm is inherently vulnerable.
Every transaction, every confidential message, every national secret transmitted online, relies on cryptographic methods that are, at their core, mathematical puzzles.
As computing power advances, these puzzles become easier to solve, leaving our digital lives exposed.
We stand at the precipice of a new era, where the very laws governing the universe might be harnessed to safeguard our most precious information.
This isn't science fiction, it's the quantum internet.
A revolutionary network leveraging the bizarre rules of quantum mechanics to create an intrinsically secure communication channel. Imagine a world where data transmitted is literally unhackable, protected by the fundamental laws of physics rather than complex algorithms. This future is not distant, it's being engineered right now, in labs and research facilities across the globe, reshaping our understanding of information itself.
The goal: to build an entirely new type of network, one that is impervious to any form of eavesdropping, a true paradigm shift for global security. The promise of the quantum internet hinges on an unprecedented engineering push. It requires harnessing phenomena like superposition and entanglement, transforming theoretical physics into tangible technology.
This endeavor is more than an upgrade, it's a complete reimagining of how information travels, from the atomic level upwards. Engineers are building the infrastructure for a network that doesn't just protect data, but makes its interception physically impossible, pushing the boundaries of what we thought achievable. This monumental task demands innovation across multiple disciplines, uniting physicists, engineers, and computer scientists in a common quest. The urgency for such a network stems from a rapidly approaching threat: the quantum computer. While still in its infancy, quantum computing promises to break through the mathematical bedrock of our current encryption standards.
Algorithms like RSA, which secure everything from online banking to government communications, would be rendered obsolete in moments.
This impending quantum apocalypse for cybersecurity means that any data intercepted today, even if encrypted, could potentially be decrypted years from now by a sufficiently powerful quantum machine. The race is on to build defenses before the attack becomes possible. To counter a quantum threat, we need a quantum solution. The quantum internet aims to provide just that, not by creating more complex puzzles, but by altering the very nature of information itself.
Instead of relying on computational difficulty, it taps into the inherent unpredictability and interconnectedness of quantum states.
This fundamental shift promises security protocols that are guaranteed by the laws of physics, making them theoretically unbreakable. The advantage is clear: if an adversary can exploit quantum mechanics, our defense must also reside in the quantum realm, creating an equilibrium of power. At the heart of quantum information lies the qubit, the quantum analog of the classical bit. Unlike a classical bit, which can only be a 0 or a 1, a qubit can exist in a superposition of both states simultaneously. This extraordinary property allows qubits to store exponentially more information than classical bits. It's the foundation for quantum computing's power and, crucially, for the quantum internet's unique communication capabilities. Mastering the control and manipulation of these elusive quantum bits is the first step in building any quantum technology, including a global network. Superposition is a cornerstone of quantum mechanics, enabling a qubit to exist in multiple states at once until measured. Imagine a spinning coin that is both heads and tails until it lands. This inherent uncertainty and multi-state potential is what gives quantum systems their immense power. In the context of the quantum internet, superposition means that quantum information is not simply transmitted as a definitive 0 or 1, but as a blend of possibilities, which adds to the complexity and richness of the data, but also to its fragility if disturbed. Understanding this state is key to building quantum communication protocols. Even more profound than superposition is quantum entanglement, a phenomenon so bizarre that Albert Einstein famously called it spooky action at a distance. Entanglement occurs when two or more particles become linked, sharing the same quantum fate, regardless of the physical distance separating them. If you measure the state of one entangled particle, the state of the other is instantly determined, no matter how far away it is. This instantaneous correlation, defying classical understanding of speed and locality, is the bedrock upon which the unhackable quantum internet will be built. This spooky action is the critical ingredient for secure quantum communication. If two parties share entangled qubits, they possess a communication channel with unique properties. Any attempt to observe or measure one of these entangled qubits immediately alters its state, and by extension, the state of its entangled partner. This disturbance is detectable, making eavesdropping impossible without detection. It's like having an alarm system built directly into the information itself, signaling any unauthorized access. This physical guarantee of integrity is what distinguishes quantum security from all classical methods. The most immediate and practical application of quantum entanglement for cybersecurity is quantum key distribution, or QKD. Unlike traditional encryption, which relies on mathematical algorithms to protect a key, QKD uses the fundamental principles of quantum mechanics to generate and distribute an absolutely secure encryption key between two parties. If an eavesdropper attempts to intercept this key, the quantum states will be disturbed, instantly alerting the legitimate users. This makes the key inherently unhackable and ensures perfect forward secrecy for encrypted communications. Let's simplify how QKD works using photons, particles of light. Alice wants to send a secure key to Bob. She encodes each bit of the key onto a single photon, polarizing it in one of several random orientations. Bob measures these photons using randomly chosen detectors. For about half the photons, their choices of encoding and measurement bases align, allowing them to establish a secure, shared key. If an eavesdropper, Eve, tries to intercept a photon, her measurement collapses its quantum state, changing its polarization, and thus altering the information before it reaches Bob. Alice and Bob can then detect these changes. The beauty of QKD lies in its unbreakability. Unlike classical encryption keys that can be brute-forced or mathematically reverse-engineered, a quantum key cannot be copied or intercepted without detection. This is a direct consequence of the no-cloning theorem in quantum mechanics, which states that an unknown quantum state cannot be perfectly copied. This theorem ensures that any attempt by an adversary to create a duplicate of the key will fundamentally alter the original, leaving an undeniable trace. For the first time, information security is guaranteed by physics itself, not by computational complexity. QKD isn't just theoretical, it's being deployed today. Governments and financial institutions are already experimenting with and implementing QKD systems for highly sensitive communications. These early deployments often utilize dedicated optical fiber links or even free-space satellite communication to transmit entangled or polarized photons. While still limited in range and requiring specialized hardware, these systems demonstrate the feasibility and immediate value of quantum-secured communication, offering a crucial layer of defense against sophisticated cyber threats. The engineering challenges are significant, but the payoff is absolute security. The widespread adoption of QKD will fundamentally neutralize current cybersecurity paradigms. Instead of an arms race between faster computers and more complex algorithms, QKD offers a definitive solution for key exchange. This doesn't mean the end of all cybersecurity concerns, but it eliminates the most critical vulnerability, the interception and decryption of private keys. With QKD, even future quantum computers capable of breaking current encryption would be unable to compromise the key exchange, securing the foundation of all subsequent communications. It shifts the battleground entirely. Beyond just QKD, the ultimate vision for the quantum internet is far more ambitious. It aims to establish a network where not just keys, but entire quantum states, including the qubits themselves, can be transmitted between distant quantum processors. This would enable entirely new applications, from distributed quantum computing to ultra-precise global sensor networks. It's about creating a quantum backbone for a future internet that can process and communicate information in ways currently unimaginable, unleashing capabilities far beyond simply secure messaging. This is where the engineering truly becomes mind-bending.
To achieve this grand vision, engineers must master quantum teleportation.
This isn't the Star Trek version of teleporting matter, but rather the instantaneous transfer of quantum information from one location to another, without physically moving the qubit itself.
It relies entirely on pre-shared entangled particles.
If Alice wants to teleport the quantum state of a qubit to Bob, she performs a joint measurement on her original qubit and one half of an entangled pair. The result of her measurement, transmitted classically, allows Bob to recreate the original quantum state on his entangled partner.
It's a marvel of physics.
While QKD and quantum teleportation are powerful, they face a significant challenge: distance. Quantum states are incredibly fragile and easily lost or corrupted over long distances, especially through optical fibers. Photons, the carriers of quantum information, attenuate and decohere as they travel, dramatically limiting the range of direct quantum communication.
For QKD, this means a typical range of only a few hundred kilometers.
To build a truly global quantum internet, engineers must overcome this inherent fragility and extend the reach of entanglement far beyond current limitations. In classical fiber optic networks, signals are boosted over long distances using optical repeaters, which amplify the signal without altering its information. However, this approach fails spectacularly for quantum information. Amplifying a quantum signal would necessitate measuring it, which, according to quantum mechanics, would destroy its delicate quantum state.
This is a fundamental obstacle. A quantum signal cannot simply be copied and rebroadcast.
A new solution, respecting the no-cloning theorem and the fragility of quantum states, is absolutely essential for extending network reach. The solution lies in quantum repeaters.
These devices don't amplify signals; instead, they generate and then swap entanglement over successive segments.
Imagine a chain. Instead of sending a photon directly from end to end, repeaters create entanglement between themselves, and then stitch these entangled links together. This process, known as entanglement swapping, effectively extends the distance over which entangled qubits can be shared, without directly measuring or destroying the quantum information.
This is one of the most significant engineering challenges and breakthroughs needed for a global quantum internet. For quantum repeaters to work effectively, they need quantum memory. These are devices capable of storing quantum states, such as the polarization of a photon, for extended periods without succumbing to decoherence. This allows repeaters to hold onto one half of an entangled pair while the other half travels, or while awaiting entanglement with another repeater segment. Quantum memory is a notoriously difficult engineering problem, requiring extremely low temperatures and precise control over atomic systems. Developing robust, long-lived quantum memory is crucial for the scalability and reliability of the quantum internet. Despite the hurdles, rudimentary quantum networks are already taking shape. Research institutions are connecting small numbers of quantum devices over short distances, demonstrating the principles of QKD and rudimentary entanglement distribution. Projects like the Quantum Internet Alliance in Europe and initiatives in the US and China are actively building proof-of-concept networks. These early steps, though limited, are vital for identifying practical challenges and refining the technologies required for a future global quantum internet, pushing the boundaries of what is possible within controlled environments. Optical fiber is the backbone of our classical internet, and it remains a primary candidate for the quantum internet. However, fibers present challenges for quantum states, especially entanglement. Photons interact with the glass, causing signal loss and decoherence. Furthermore, the distance limitations require an extensive network of quantum repeaters, each a complex piece of engineering. While fiber offers a controlled environment, developing low-loss quantum-compatible fiber and efficient repeater technologies remains a significant engineering hurdle. Researchers are exploring various wavelengths and fiber types to minimize these issues. To bypass the limitations of optical fiber, researchers are also exploring free-space communication, where photons travel through the atmosphere or even the vacuum of space. Satellite-based QKD has already been demonstrated by China's Mishias satellite, successfully establishing entanglement between the satellite and ground stations thousands of kilometers apart. This approach offers the potential for truly global quantum networks, transcending terrestrial distances. However, atmospheric turbulence and weather conditions can significantly impact signal quality, posing their own unique engineering challenges for reliable operation. Building a quantum internet requires not just hardware, but an entire quantum stack of protocols and software. Just as the classical internet relies on TCP/IP, the quantum internet will need its own set of rules for routing, error correction, and application development. This means developing quantum network nodes, switches, and interfaces that can manage and interpret quantum information. This software layer is critical for making the complex quantum hardware accessible and usable for a wide range of future applications, creating an entirely new field of quantum network engineering. Many quantum devices, especially those designed for processing and storing qubits, operate only at extremely low, cryogenic temperatures. Superconducting qubits, for example, require temperatures near absolute zero, colder than deep space. This presents enormous engineering challenges for scaling up. Imagine an internet infrastructure where every repeater or node needs its own superchiller. Miniaturizing and making these cryogenic systems efficient and reliable is crucial for widespread deployment. Researchers are also exploring alternative qubit technologies that can operate at higher, more manageable temperatures, like those based on silicon. Quantum information is incredibly fragile, making it prone to errors from environmental noise and imperfections in devices. Unlike classical information, which can be easily copied and redundantly stored for error correction, quantum states cannot be simply duplicated. This necessitates a unique approach, quantum error correction. This complex field involves encoding quantum information across multiple entangled qubits in such a way that errors can be detected and corrected without directly measuring the original information. Developing robust quantum error correction codes is paramount for reliable quantum communication over long distances. The immense strategic implications of the quantum internet have ignited a fierce geopolitical war between world powers. The nation that masters this technology first will possess an unparalleled advantage in cybersecurity, intelligence gathering, and military communications. The stakes are incredibly high: economic dominance, national security, and global influence. This isn't just a scientific race, it's a cold war of innovation, with billions of dollars being poured into research and development by competing nations, each vying to be the first to achieve quantum supremacy in this critical domain. The United States, recognizing the critical importance of quantum technologies, has launched the National Quantum Initiative. This multi-agency program aims to accelerate quantum research and development, fostering collaboration between government labs, academia, and industry. Key areas of focus include building quantum computers, developing quantum sensors, and, crucially, establishing a national quantum internet infrastructure. The U.S. seeks to maintain its leadership in scientific innovation and ensure its defense capabilities are future-proof against quantum threats, while also developing its own offensive quantum capabilities. China has emerged as a formidable force in the quantum race, investing vast resources and achieving significant breakthroughs, particularly in quantum communication. With projects like the Michias satellite and the world's longest terrestrial QKD network, China has demonstrated its intent to lead. Their strategy involves large-scale, coordinated national efforts, rapid deployment of experimental systems, and a focus on both fundamental research and practical applications. China's ambitious drive for quantum supremacy is viewed by many as a direct challenge to the technological leadership of the West, raising geopolitical tensions. Europe is responding with its own concerted effort, the Quantum Internet Alliance, a collaborative initiative pooling expertise and resources from across the continent. The goal is to build a pan-European quantum internet, connecting quantum processors and users from different member states. By fostering strong academic and industrial partnerships, Europe aims to create a robust quantum ecosystem, focusing on developing open standards and interoperable technologies. This collaborative model is seen as crucial for tackling the immense scientific and engineering challenges, ensuring Europe remains a key player in the global quantum landscape. The race isn't limited to these major players.
Countries like Canada, Japan, Australia, and South Korea are also making significant investments in quantum technologies, recognizing the strategic imperative. These nations are developing their own research programs, building specialized labs, and seeking international partnerships to secure a foothold in the quantum future. The global competition fosters rapid innovation, but also raises concerns about potential technological fragmentation and the creation of isolated quantum networks, rather than a truly unified global infrastructure, complicating future interoperability. The term quantum supremacy often refers to a quantum computer performing a task that a classical supercomputer cannot, or would take an impractically long time to complete. In the context of the quantum internet, achieving quantum supremacy means mastering the ability to transmit and process quantum information with capabilities far beyond any classical network. This includes achieving entanglement distribution over vast distances, robust quantum memory, and error-corrected quantum communication. It's about demonstrating a decisive advantage in quantum information exchange, rendering classical methods inferior. The military implications of quantum supremacy are profound. An unhackable quantum internet would revolutionize secure military communications, ensuring that classified information remains absolutely protected from adversaries. It would enable encrypted command and control networks, impervious to even the most advanced interception techniques. Furthermore, quantum sensors could provide unprecedented capabilities for detection and surveillance. The ability to launch and defend against quantum-era cyberattacks will be a defining factor in future geopolitical power dynamics, making this a top priority for defense ministries worldwide. Beyond national security, the economic stakes of the quantum internet are immense. The first nations to successfully deploy and commercialize quantum communication technologies will gain a significant advantage in finance, trade, and intellectual property protection.
Industries from banking to healthcare rely heavily on secure data transmission. A quantum-secured network promises to protect these vital sectors from cyber espionage and fraud on an unprecedented scale. The quantum internet is poised to create new industries, jobs, and market opportunities, making it a critical component of future economic growth and competitiveness. The geopolitical race also raises concerns about a quantum divide. Nations without the resources or expertise to develop quantum technologies could find themselves at a severe disadvantage, lacking access to cutting-edge security and communication infrastructure. This could exacerbate existing global inequalities, creating a two-tiered internet where some nations operate with absolute quantum security while others remain vulnerable to classical and even quantum threats. Bridging this potential divide will require international cooperation and technology transfer, a challenging prospect in a competitive landscape. The journey to a fully functional global quantum internet is a multi-stage roadmap. The first stage, which we are in now, focuses on QKD deployment for secure key exchange over limited distances. The second stage involves developing quantum repeaters to extend entanglement distribution over hundreds of kilometers. The third and final stage envisions a fully interconnected quantum internet capable of transmitting arbitrary quantum states between quantum processors, enabling a wide range of advanced applications. Each stage presents unique engineering and scientific challenges, requiring sustained investment and innovation. Another critical engineering challenge is the development of quantum transducers. These devices are necessary to convert quantum information from one physical medium to another, for example, from superconducting qubits in a quantum computer to photons in an optical fiber. This interconversion is crucial for integrating different quantum technologies and for bridging the gap between quantum processors and the quantum network itself. Without efficient and low-noise transducers, the quantum internet would be a collection of isolated islands, unable to communicate effectively. Just like the classical internet, a quantum internet will require sophisticated network nodes and switches to route quantum information. These devices must be able to receive entangled qubits, perform entanglement swapping, and forward quantum states to their intended destinations, all while preserving the fragile quantum coherence. Building quantum-compatible switches that can handle multiple quantum channels simultaneously is a complex engineering task, requiring advances in quantum optics, material science, and cryogenics.
These nodes will be the traffic cops of the quantum superhighway.
The quantum internet will not entirely replace the classical internet, instead, it will integrate with it, offering enhanced security and new capabilities. Much of the control and management of the quantum network will still rely on classical computing and communication. The challenge is to design seamless interfaces that allow quantum and classical systems to work in harmony, leveraging the strengths of both. This hybrid approach will be crucial for the transition phase and for developing applications that combine quantum security with classical data processing, creating a more robust and versatile overall infrastructure. Beyond communication, the quantum internet will also enable distributed quantum sensing. Entangled networks of quantum sensors could achieve unprecedented precision in measurements, far exceeding the capabilities of classical sensors. Imagine a global network of entangled atomic clocks for ultra-precise navigation, or highly sensitive magnetometers for medical diagnostics and geological surveys. These distributed quantum sensors would leverage entanglement to overcome noise and enhance sensitivity, opening up entirely new possibilities for scientific discovery and technological innovation across various fields. The ultimate goal for the quantum internet is to enable distributed quantum computing.
This means connecting multiple quantum computers or quantum processors together to form a larger, more powerful computational resource. By sharing entangled qubits and quantum information, these distributed systems could tackle problems too complex for even the largest standalone quantum computers. This collaboration could lead to breakthroughs in materials science, drug discovery, and artificial intelligence, unleashing a new era of computational power and fundamentally changing the landscape of problem solving. The sheer scale of building a global quantum internet presents unprecedented engineering challenges. Deploying millions of quantum repeaters, ensuring coherence over thousands of kilometers, and managing a vast network of extremely sensitive quantum devices requires innovation on a grand scale. The current prototypes are delicate, expensive, and temperamental. Scaling this technology to a global infrastructure comparable to our classical internet demands breakthroughs in miniaturization, cost reduction, and robust design.
It's a colossal undertaking, requiring sustained global effort and collaboration. The development of the quantum internet represents a quantum leap in human technological capability. It's not just an improvement, it's a fundamentally different way of handling and transmitting information. This shift will redefine our understanding of security, communication, and computation. It moves us from a world of probabilistic security, where encryption can eventually be broken, to a world of absolute, physics-guaranteed security. This is a profound transformation, echoing the impact of the classical internet itself, but with an even more foundational change to information processing. As with any global network, standardization will be crucial for the quantum internet. Different research groups and nations are developing their own quantum hardware and protocols, which could lead to incompatibility. Establishing international standards for qubits, entanglement distribution, quantum repeaters, and network protocols will be essential to ensure that a truly global and interoperable quantum internet can emerge. Organizations like the ITU are beginning to address these challenges, but achieving consensus across competing geopolitical interests will be a delicate and lengthy process. While the quantum internet builds absolute security, research is also underway on post-quantum cryptography, PQC. These are classical algorithms designed to be resistant to attacks from quantum computers. PQC is a crucial stopgap solution, as it can be implemented on existing classical infrastructure, protecting current data until a full quantum internet is established. However, PQC still relies on mathematical hardness, unlike QKD's physical guarantees. Both PQC and the quantum internet are complementary approaches in the battle against future quantum threats, addressing different time horizons and infrastructures. The race to develop a quantum internet is intensifying daily. Each major breakthrough by one nation fuels renewed efforts by others, creating a virtuous cycle of innovation and competition. This geopolitical struggle isn't just about who gets there first, it's about who defines the standards, controls the intellectual property, and ultimately, wields the power of this transformative technology.
The stakes are too high for any nation to sit idly by, ensuring that investment and scientific endeavor in quantum information science will only continue to accelerate in the coming decades. While global networks are the ultimate goal, early quantum internet deployments are likely to be regional, connecting key metropolitan areas or government facilities.
Cities with high concentrations of data centers, financial institutions, and research labs will be prime candidates for these initial networks. Imagine quantum-secured links between banks, stock exchanges, and government agencies within a city. These urban quantum networks will serve as crucial testbeds, refining the technology and demonstrating its practical benefits before wider national and international expansion can take place, segment by segment. The full realization of a global quantum internet will have a profound impact on nearly every aspect of our lives. From ultra-secure online banking and communication to privacy-enhanced health records and national defense, its reach will be pervasive. It promises a world where digital information is truly safe, freeing us from the constant threat of sophisticated cyber attacks. This secure foundation will foster innovation, enable new forms of commerce, and redefine the boundaries of what is possible in our interconnected world, leading to a new era of digital trust. Ultimately, the quantum internet represents our boldest attempt to secure the future of information. It's a testament to human ingenuity, pushing the limits of physics and engineering to build a network that is inherently unhackable. The journey is long and fraught with challenges, but the potential rewards, absolute security, unprecedented computational power, and revolutionary sensing capabilities, make it an endeavor worth pursuing. This is more than just a technological upgrade, it's a refoundation of our digital world, built on the very fabric of reality itself, a quantum leap for humanity. While QKD offers unhackable key distribution, scaling it to a global network poses significant challenges. Each QKD link is point-to-point, requiring dedicated fiber or free-space connections. For a widespread network, this means an immense proliferation of individual QKD devices, creating complex infrastructure requirements. Integrating these secure links into a seamless, accessible network is a massive undertaking. The goal is to move beyond isolated QKD deployments to an integrated, routing-capable quantum internet where quantum keys can be established on demand between any 2 points, globally. Let's delve deeper into entanglement swapping, the core mechanism for quantum repeaters. Imagine 3 stations, A, B, and C. Station A creates an entangled pair, sending 1 qubit to B. Station C also creates an entangled pair, sending 1 qubit to B. Station B then performs a special measurement on the 2 qubits it received, one from A, one from C. This measurement swaps the entanglement, so now the qubits remaining at A and C are entangled, even though they never directly interacted. This chain reaction allows entanglement to be extended over arbitrarily long distances, segment by segment. Building the quantum internet requires highly efficient and reliable quantum emitters and detectors. Emitters generate single photons in a controlled quantum state, often entangled. Detectors, on the other hand, must be exquisitely sensitive, capable of registering single photons, even after they've traveled long distances. These components are at the cutting edge of photonics engineering, requiring robust and stable operation at various wavelengths and temperatures. Advances in these foundational technologies directly impact the range, speed, and fidelity of quantum communication links. The Quantum Internet Alliance, a consortium of over 40 academic and industrial partners across Europe, is a prime example of collaborative efforts. Their mission is to develop a full-stack quantum internet, from hardware to software, within Europe. They are focusing on key technologies like quantum memory, transducers, and repeaters, aiming to build a functional prototype network. This collaborative model, sharing expertise and resources, is considered vital for overcoming the multidisciplinary challenges inherent in building such a complex system, accelerating progress beyond individual national efforts. China's strategic approach to quantum communication is exemplified by its operational national quantum communication backbone. This network, spanning thousands of kilometers, already integrates terrestrial QKD with satellite links, showcasing a hybrid infrastructure. It serves as a testbed for future quantum internet technologies and has demonstrated secure communications for government and financial sectors.
This aggressive deployment, coupled with significant investment in fundamental research, positions China as a leader in practical quantum communication applications, highlighting their focus on immediate strategic advantages.
In the United States, several initiatives are working towards a national quantum internet.
The Department of Energy, for instance, is establishing quantum internet testbeds at its national labs, focusing on developing the core technologies and protocols. Universities like Caltech and Argonne National Laboratory are spearheading projects, exploring different architectures and qubit technologies. The U.S. approach emphasizes fundamental research, building a strong scientific foundation while also focusing on integrating existing classical infrastructure with emerging quantum capabilities, ensuring a robust and versatile future network. One promising avenue for developing robust quantum repeaters and memory involves quantum dots. These artificial atoms can emit single photons and retain quantum information for relatively long periods. Their ability to interface with light makes them ideal candidates for generating and transmitting entanglement across optical fibers. Engineering quantum dots to operate efficiently and reliably at scale is a complex material science challenge, but breakthroughs in this area could significantly advance the development of practical quantum network components, moving closer to deployable quantum repeaters outside of lab conditions. Another major player in the qubit landscape is superconducting circuits. These qubits, often used in quantum computing, are highly controllable and scalable within cryogenic environments. While excellent for processing, coupling them efficiently to photons for long-distance communication is a significant challenge, necessitating high-performance quantum transducers. The integration of superconducting qubits with quantum network infrastructure is crucial for realizing distributed quantum computing, as these are the processing units that will ultimately perform the complex quantum calculations across the network.
Trapped ions offer another promising platform for quantum memory and processing.
Individual ions are suspended and manipulated by electromagnetic fields, providing excellent coherence times and control fidelity. These systems are highly suitable for high-fidelity quantum operations and as nodes in a quantum network, potentially serving as quantum repeaters. The engineering challenge here lies in scaling these highly precise systems to a larger number of ions and creating robust interfaces for photonic communication, allowing their quantum states to be effectively shared across the network. The vision of a global quantum internet is not merely about connecting a few labs, it's about building a backbone capable of supporting a new generation of secure and powerful applications. This backbone will connect quantum processors, quantum sensors, and quantum memory systems across continents, enabling unprecedented capabilities. Achieving this requires overcoming not just the scientific and engineering hurdles, but also the logistical and political challenges of international collaboration, ensuring that disparate national efforts can eventually converge into a truly global infrastructure for quantum information.
The most tangible and immediate benefit of the quantum internet, as previously highlighted, is its promise of absolute information security. In a world increasingly reliant on digital data, where cyber attacks are a constant threat, the ability to transmit information that is fundamentally unhackable is revolutionary. This applies not only to government secrets and financial transactions but also to personal data, medical records, and intellectual property. The quantum internet offers a defensive shield against any future computational power, ensuring privacy and integrity for critical data. Building the quantum internet isn't just about the physical network, it's about fostering an entire ecosystem. This includes developing quantum software and applications, training a new generation of quantum engineers and scientists, and creating businesses that can leverage this technology. From quantum software developers to hardware manufacturers and service providers, a new industry is emerging. This ecosystem will drive the innovation necessary to make the quantum internet a reality, translating complex physics into user-friendly tools and services that benefit society at large. As with any powerful technology, the quantum internet raises ethical considerations. While it promises unparalleled security, it could also potentially enable new forms of surveillance or control if misused. The power of unhackable communication must be balanced with democratic values and individual privacy rights. International agreements and regulatory frameworks will be crucial to guide its development and ensure its benefits are shared equitably and responsibly.
These discussions need to happen now, as the technology is still in its formative stages, to prevent future misuse.
The journey to a fully functional, global quantum internet is an odyssey that will span decades.
It demands sustained research, groundbreaking engineering, and unprecedented international collaboration amidst intense geopolitical competition. Yet, the vision of an unhackable network, leveraging the most profound mysteries of physics, is a powerful motivator. It promises to redefine our digital future, offering a new bedrock of security and ushering in an era of information exchange previously confined to the realm of imagination.
The laws of information are indeed being rewritten. The quantum internet is far more than just a superior encryption tool. While QKD provides an unbreakable key, the full quantum internet will allow for entirely new classes of applications leveraging entangled states. Imagine cloud quantum computing where data never leaves its quantum state, or secure voting systems intrinsically verifiable by physics.
It opens doors to novel distributed algorithms and communication paradigms that go beyond simply securing bits, but rather manipulating and transmitting quantum information directly, creating a truly quantum advantage. While security is paramount, the quantum internet also offers potential advantages in speed for certain tasks. The instantaneous nature of entanglement, while not enabling faster-than-light communication of classical information, does allow for immediate correlation across distances.
This could mean faster key establishment or more efficient synchronization for distributed quantum computing.
It's a subtle but powerful difference, where the inherent properties of quantum mechanics provide an edge not achievable through classical means, transforming certain aspects of network efficiency and responsiveness. Just as crucial as repeaters are quantum routers. These devices will be capable of receiving quantum information from multiple input ports and routing it to the correct output port, maintaining entanglement and coherence throughout the process. A quantum router would need robust quantum memory, sophisticated control systems, and the ability to perform entanglement swapping to redirect quantum paths. This represents a monumental engineering feat, as each router needs to operate without reading the quantum information it handles, ensuring its integrity and security.
Universities and academic institutions play a foundational role in the quantum internet revolution.
They are the incubators for groundbreaking theoretical physics, the training grounds for future quantum engineers, and the sites of much of the initial experimental breakthroughs.
Collaborations between academia and industry are vital for translating fundamental research into practical applications.
Without the continuous flow of new ideas and skilled talent from universities, the quantum internet would remain a distant dream. Their contributions are the lifeblood of this complex scientific and engineering endeavor. The industrial sector is rapidly increasing its involvement, recognizing the enormous commercial potential of the quantum internet. Tech giants and startups alike are investing in quantum hardware, software, and services.
Companies are developing specialized components like single photon sources, detectors, and cryogenic systems.
This industrial push is critical for moving quantum technologies from the lab to commercial viability, driving down costs, and scaling production. It's the engine that will turn theoretical concepts into deployed, accessible infrastructure, making the quantum internet a reality for businesses and consumers. The complexity of quantum repeaters cannot be overstated. A single repeater station involves sophisticated lasers, high-precision optics, quantum memory units, and entanglement swapping modules, often operating in cryovacuum environments. Each component must function with extraordinary fidelity to maintain the delicate quantum states. Engineers are designing different generations of repeaters, with increasing capabilities for entanglement distribution distance and rate. This iterative design and testing process is fundamental to the long-term success of building a robust, long-range quantum network, addressing each challenge systematically.
Despite geopolitical rivalries, global scientific collaboration remains essential.
Researchers from different nations often publish their findings, attend international conferences, and even collaborate on specific projects. This open exchange of knowledge is vital for accelerating progress in such a complex and challenging field. While nations compete for supremacy, the underlying scientific endeavor thrives on shared discovery. Balancing competition with collaboration is a delicate dance, but one that is ultimately necessary for humanity to collectively harness the full potential of quantum information.
The quantum internet will not arrive overnight, but its eventual impact will be transformative.
It promises a future where our most sensitive data is truly secure, where computational power is distributed globally, and where scientific discovery is accelerated by unprecedented sensing capabilities.
This is a journey to harness the most counterintuitive aspects of reality for the betterment of humanity.
The unhackable quantum internet, powered by Einstein's spooky action at a distance, is not just a technological dream, it is an engineering reality being built, qubit by qubit, entanglement by entanglement.